Thank you. Thanks for introduction. I'm very honored to be here. On my way here, I flew from South Korea, like 10 hours, a very light flight. And of course, I watched several movies, and one of them was Challenger. I knew it's about the tennis match. I didn't know it was about Stanford. It's what a coincidence, right? Today, I'll be talking about this a little bit mouthful topic, and then I also learned this morning I'll be the obstacle between you guys and dinner, but I have 30 minutes given to me, so I'll try to utilize all 30 minutes I have, now 29 minutes. Okay, usually I update my presentation based on the discussion of the day, and if I'm allowed to summarize today's topic, all the talks, and I can give you 5 keywords, which is domain expertise, RAG, multi-modal, and reinforced learning, and knowledge graph. And then if I add 3 more, small LLM, edge computing, and agent. I have all these 8 keywords implemented in my slide because I had the vision, what will be happening today. So I'll talk about that. And also, I'll throw some of the talk code this morning and afternoon, for example, AI Alliance and iAutomatic, mine that they are still here, okay. And then IBM, Tel, NVIDIA, Exelos, a lot of partners from industry, and also JSR, and then to this morning's talk from Tom, Dimitri, and Professor Mitra, who complained about the data sharing. I'll mention about that a little bit. Okay, so let's get down to it. People were asking who the first time were seeing me, what is my position, what I'm doing. So my goal is to achieve this fully autonomous fab. So it is called lights out manufacturing, but it's not about getting rid of the people, engineers. It is more making them more powerful. So it is analogy between the autonomous driving versus autonomous fab, meaning there's not much human involved needed, but actually it's the behind the scene, people can do more stuff rather than just replacing the knobs and the boards and so on. So if you look at it, to have this all autonomous fab, what you need is 3 basic components: sensing, analysis, and control. Because you have to see what is happening or hear or smell, whatever sense you can utilize, and you should be able to analyze, and then execution is really important. You have to do something about it, right? That's a summary of autonomous fab. And I can say this is very similar concept, OODA, observe and orient, decide, and action is actually control. I sense that some of you now coming from the semiconductor industry, so I added a little bit of introduction about the equipment process control of today, or sometimes yesterday. That chart is about what you call a trace data, very typical chart, what you can see when you monitor equipment behavior. The x-axis is the time, so usually 1 second. Every second, and there are points going up and down. The blue color is what for example, this is edge device, and I just showed the 2 sensors. One is reflected power, blue color, and one is forward power is red color. That means at some point, you initiate the plasma, and then something is happening, and actually that is etching, and then you cut out the plasma, so etching is done. This is very simple recipe. And here, example, there are 2 steps of etch. What we do, because it's a little bit even just only 2 steps, it's very complicated to monitor all these signals. Every second's data is too much and huge. So what we do, we just cut out a couple of steps. And then, okay, it works great. We capture the snapshot of that step. For example, this case, for the forward power, the red color, we just capture the average value or standard deviation, the mean or max. And for reflected power, on top of those 4, we add initial slope and stability and so on. This is conventional way. And if you are more sophisticated, you go a little bit further. Not only relying on the 1 step, by the way, the green color is just giving you the number of the steps. So you can tell this is just only 1 step. So you can summarize all the signals with use this basic statistics. And if you go a little further, you can trim down the window. Instead of having the full step observation, you just only observe the time you needed. And so you make a little bit different. And in order to do this, what you need to have all the domain expertise, knowledge, experience. As of today or yesterday, a lot of manual efforts were needed. All of this can be reduced and simplified and further enhance using LLM, Gen AI, and so on. That will be the main topic. I'll give you the spoiler alert. It is the summary of all the topics I'm going to give you today. If you look at one specific equipment, I would say the trace, the chart I showed before, that's the main part of the equipment control. And then summary is what I showed you, snapshot of certain step or a certain window. But it's not only those two data. We have a lot of information about events, what happens. Sometimes tool goes wrong, and we need to know exactly what happened. There's alarm. So all those events and information are needed. And of course, equipment is not just a 3D printed one material thing. There are complicated stuff embedded and assembled together. So a lot of different histories, and there is the knowledge base. So all of this needs to be network connected using the knowledge graph and so on. And what is our goal? Is trying to understand what is happening and predict what will happen. And if we know both of them, we have to control. And then we are deeply not rely on testing, reinforcement learning as one of the best tools we can utilize in terms of control. So once we can do this, we'll be able to do APC. This is the advanced process control. One example is like this. So there are a lot of the photo, print out the pattern, and you're actually etching away. That process repeated over and over again. So let's say your photo print out a little bit wider than you're supposed to have. Then what will happen? You just clean it up and deposition the new material, like the JSR material, new photoresist, you print again. Then you have to spend a lot of time and resource and so on. Or simply, if you knew your CDs or the dimension circuits are a little bit wider than expected, you etch less if you know what happened. So this advanced process control can reduce work and resource, make it much faster and efficient. And same goes for chamber matching or yield prediction and so on. So this will be the main topic of use cases I'm going to talk today. Okay, since I knew a lot of people are very experts in terms of AI, I'll skip through this general conventions. Here, I'm trying to just say is generative AI is really important, and then right now, multimodal is even more important. And this plot, I guess one of the most famous plots presented this year from many people. Source from Bloomberg. Our projecting is 10 years, this Gen AI market will be exponentially grow. And then I added some chart about the multimodal AI market. But the thing is, this estimation was done before release GPT-4 only. So you can only imagine that it will be much more higher in terms of demand and market revenue. And then I need to skip this one. This one, this very simple schematic of the rack and the multimodality. So I don't need to go into detail, but this one I'm reusing a lot about this text and audio is like waveform and video or images. So this will be one of the main key parts I'll be using in this topic. Okay. So all this concept and technologies, how we're going to use for semiconductor industry. If you know about semiconductor industry, it's not about just processing equipment, utilizing equipment to print it out some patterns out of the chip. First, you have to start with the design involving layout and a lot of process control. So do you know how many process steps you need for that? For example, 5 nanometer technology in terms of logic. How many process steps? Can you guys guess? Yeah, close to 1,000. It depends on which fab you're talking about, right? If 1,000 steps are there, it's really difficult to have all of them controlled, optimized properly. So we are talking about yield at least 80% to be profitable. It's really a long way to go. So it was relatively easy long time ago, like 28 nanometers and 14 nanometers, even 7 nanometers. But down to 5, 4, 3 is really difficult. It is really important to have the good technologies utilizing and process control. And in order to have the good process control, we have to inspect. So we need a lot of metrologists and process development, inspection, and prediction. All of those are needed, and it's a very good use case for Gen AI. Okay, so I showed this before, multimodal foundation model. So if I just add one more component, for the semiconductor manufacturing, which is called time series, because as I showed you, the basic concept of the controlling the equipment is based on sensor data, how we're going to control, how we're going to forecast what will happen, and so on. So very similar. So it's conceptually, it's not that different. I'm just adding one more component in terms of foundation model. Okay, so to build that kind of foundation model, what are needed? So it's very similar to what Semicon does. Like we have a lot of information on process, and equipment, operation, and analytics. It's the different type of the knowledge and different type of resources like the text, image, and tables, and so on. A lot of different type of the data sources. So all combined, we are using multimodal foundation model, and we go through a lot of pre-training and fine-tuning and so on, use a lot of different techniques and racks, COT, and length chain, and so on. So all of these are needed, and as you can guess, every day there's new technologies coming on. So we have to try out a new technology almost daily basis. This is the first example I'm going to give you. I think the one of the talk mentioned similar concept. I just cannot find that. I wrote somewhere, but for the wafer perspective, you really want to know what happened in the wafer history, and when it goes to what kind of tools and what happened. But for the equipment engineer perspective, they don't care about what happens to wafer. They only care about equipment itself, whether it behaves as it's supposed. So that changes the viewpoint completely. So equipment, the engineer perspective, they don't need to know exactly what kind of history they need to go through in terms of wafer. All they need to know, chamber A, sensor A, is behaving correctly. Chamber B, same sensor A, but they name it differently so that they can tell the same sensor A happened where and when and what. But if you look at the wafer, you need the big data, and sensor A does very similar thing throughout all different tools, all different chambers. You need to know they are the same thing, but they're a little bit different differentiation. So before, we utilized a lot of training to engineers. When you name it, please follow these rules. If you don't follow, you will have some kind of difficulties or penalties and so on. But as nature, human nature, we tend to make all right. Okay. We tend to make errors. Let's say you are 99% time is accurate, and you miss only 1% error. Then imagine that there are 100 different chambers, and then there's 1,000 different steps. Only 1% error. If you accumulate all of them, they're huge. So we have to do all this manually. This is a very huge nuisance task. But with LLM and knowledge graph, I think so. I think I need to switch. Is it okay? Is this better? All right. We can utilize knowledge graph and LLM and to make the alignments automatically. 1% error is okay. We can handle it. We can take over from here. Another example. So we talked about engineering expertise, subject matter expertise, domain expertise. All of them is not only about physics textbook, engineering note, and so on. There are a lot of histories written all over the places nearby the equipment, because when engineer does something, they write down what happened. But it's very unstructured form. Just everywhere, everybody does a different way. There is a discipline, but not everybody follows exactly same rules, same concept, same language even. Before, we are not able to utilize all those very precious information. And if you want to throw them into database, it will be huge because of unstructured data. It's really difficult to utilize it. But with LLM, it's way easier, much better. So this is actually the engine we actually built. This is a translated version of this engine. For example, the engineer just prompted, I got error ABC, what should I do or what happened before? Then engines, LLMs give you the answer, what happened before, and give you suggestions what you have to do based on history and so on. This is already happening, it's not the future. We already have this kind of service in place. And this one utilizes all the images, text, and graphs, and so on. So it's really multimodal. And this is another example. This is the same as the trace data, but a lot similar. The reason we have this duplicated charts over and over again is because the technology evolves very much. Now, the simple etch won't cut it because it's so sophisticated, so small, and we have to make it very deep. what we do is we etch and dab within the same chamber, within the same recipe. You can see that this kind of the behavior repeated over and over again, but this is just the same recipe. So it's very complicated. Imagine then you capture snapshot of all this. Somehow you have to make a difference between the first chart, second chart, third chart, and so on. So it's just way beyond the human's basic capability. This is where foundation model, multi-modal kicks in very well. And this is one example. If you can tell the difference between blue color trace versus red color, what's the major differences? Of course, color is different. I color differently. Okay, yeah, like this. It's not the rocket science. It's not exact measure, but at least you can tell that this kind of behavior is slightly different, blue versus red. And you'll be able to tell because I color differently. The original data coming from the equipment is just everything is black color, right? So it's really difficult for engineers to tell the difference. So all this minor anomaly detection needs, we have to go through a lot of machine learning, AI, especially Gen AI is important because especially this kind of behavior we haven't seen before. Okay. Another example is the bottom. I'll go more details in the next slide. So this is the chart coming from something called OES, optical emission spectroscopy. So when there is plasma, we have the sensors which observe the light, what is happening inside the chamber, and you show the intensity. So this axis is about the wavelengths, and this axis is about time, and z-axis about intensity. So if you just cut this way, it will look like this or this. I said wavelengths is the part. You can see a lot of peak, meaning some like N2 peak, O2 peaks, different chemicals. It detects what is happening. And if you look at the progress of intensity by time, you can tell, oh, O2 is larger in terms of intensity and drops to a certain point. So we make the decision when to stop etching based on this kind of curve. This is the very typical process, what you call EPD, endpoint detection. Before today, yesterday, or many fabs here right now are doing is you have to know exactly what peak you have to monitor. So it's predetermined. And then just only collect that peak time data. So only this one, for example. And then make the decision when you're going to cut the recipe. But like this example, same species, intensity can vary. You never know exactly which one will be better. Sometimes this peak is a better indicator, sometimes this one, or sometimes this one. But since you are utilizing predetermined species information, there's no way you can change it in the middle of the process. But with the Gen AI and AI, we can just use the whole three-dimensional plot as it is and make the decision on the fly. So there's a big difference in terms of analytics. So not only that, so for human eyes, it's easier to check what are the peaks. I made the red dots on the peaks. But from the machine perspective, it is not that easy. So there are numerous algorithms to detect these peaks. And algorithm is a little bit, you need update once in a while, and is not concrete and absolutely correct. So you have to add a lot of learning. So AI is better suited in terms of peak identification. This is one example. So we found very small peak here, right next to usual suspect. And then most of days, we just don't do anything because this is very small peak. Let's just ignore them. But it turned out those are peak related N2. So there was a leak. We are not supposed to have that kind of gas. So sometimes we are able to detect, but very small amount. So with AI technology, we are able to check what happened and to prevent any further losses. And this is another typical examples. So RCA means root cause analysis. When you look at the wafer, I said there are many steps like the metrology and the inspection. Once in a while, so out of 1,000 process steps, like 20% to 30%, there are metrology steps. Because it's so complicated, you have to check whether it is going as is planned. So you look at the wafers, take picture of entire wafer like this. And these red dots are suspected defects, which means you're supposed to have some level of patterns, but it looks way different than patterns. We make this kind of the red dots. Then this is the first view. And then you cannot tell, just looking at the red dot, what kind of defects they are. You have to zoom in one individual defect and make it like this blowout so that you can determine what they are. For determining what kind of defect it is, we used rules before. Oh, that one has to be something based on the experience and knowledge and so on. So whenever there's a new defect, there's a question. But the thing is, you take a picture of the entire wafer and physically zoom in and look at this one takes time. Imagine that usually there are more than 1,000 defects. So you cannot do all 1,000 times. So you only select some of them. So we are missing a lot of steps. If we are able to just determine what kind of the defects they are, just based on this, that will be a lot of energy resource saving. And another example is the yield analysis. This is not clearly seen here, just the wafer and test, yield test, and then showing some kind of patterns. So we just, instead of looking into all those analytics, we just typed prompt. So we have some kind of errors. Is this happened before? And if it happened, what was the root cause and what we should do? So this multimodality and LLM gives you the, it's not exactly correct answers because we are also suffering from the hallucination and incorrect answers and so on. But still, we're trying to make the best out of it, utilizing RAG and, oh, time out already. Oh, I still have 8 minutes left. Okay, this is great use case of the LLM again. And this one is combination of the many information. So X is as a function of the input, so you use recipe information. So how far, how high you have to control your power, what kind of gases you have to use, all those information, and wafer history, equipment history, all those used as an input, and we use physics. As our physics from neural network is one of the way we can utilize physics. And then we try to predict CD, which is the width of the circuitry, and the profile and defects and so on. Because the signal to noise ratio is enormous, because we have only handful of wafers, but there are so many different inputs, very small number of output. So it is really difficult to make out of it. So this machine learning with the very small sample set is one of the ways we have to utilize, and one of the reasons why we are using PINN physics, because we have to cut down the signal to noise ratio as much as possible, and we have to utilize information we already know. Okay, so now I'm going down to time series foundation model. If you look at multimodality, multimodal large language model, majority of them, they are encoding based on the text or waveform, like the audio, sound, and image, and so on. Not so much of the time series data yet. There are many different SOTA model claimed, and this is one of the good paper published a couple of months ago. It's about the survey of all these different time series model. So we look at all those things. This is just example of the several selected, like patch TST from IBM and time LLM and SOAPs and the time GPT. So we utilize all these different kind of the time series model and try to apply to our trace data, the one I showed in the earlier, this talk. This is example. We are able to get down to very decent result, but the major obstacle is like this. When there is a step function-like behavior, as you can see, the pink color is not exactly flat. So there is quite off. Even though it looks similar in terms of pattern, it's not quite there yet. And the bigger problem is the time delay or time lag. It doesn't predict when it goes up very fast. So there is always a couple of seconds delays or a couple of points, something seconds of delays. Those two are major obstacles we are facing right now when we utilize the current existing time series foundation model. So when we first tried with the zero shot, as you can see from the left-hand side chart, is no way closed. It's very bad. But after a couple of pre-training, we are able to have the decent prediction, and the fine-tuning or full fine-tuning is quite reasonably good. If you just look at the chart itself, and MA value is real low, but will you able to use it? No. The thing is, as I explained before, we want to use information around this area or this area. So if you look at them, correlation, R square is maximum 0.8, usually less than 0.5. So there's no way we can utilize that kind of correlation for the prediction capability. A lot of the expertise we need to learn. So that's why we try to collaborate a lot of the different companies, and IBM is one of them, and AI Automatic is another companies, and Minds AI, and so on. And this is a very interesting example of utilizing the knowledge graph. What happened was one equipment signal from this blue color jumped to the red color all of a sudden after equipment maintenance. So when you do the equipment maintenance, engineers compare before, after, and the previous maintenance, all those charts. And they are not able to find any different signals at all. They came to us, can you tell any differences? So we went through a lot of different technologies and community search, and one is the good knowledge graph. So we are able to build some kind of the network out of it. So before, good, and after, bad. So we are able to find a couple of sensors behave slightly different. It's not the value is different, the network are different. We went to the experts, so why is it possible? It turns out the outside the chamber, inside the chamber, but outside the reaction area, there is some kind of the membrane that controls a little bit of the outcome. Nobody looked at that before, but there was a little bit of change of the depth value that made a huge difference. And that kind of analysis cannot be done with conventional analytics. Network and knowledge are one of the key components of this one. And this is another interesting one. Whenever you use RF, which you use the matching. So radio frequency, there is a generator, and there's a transmission line, and there's a matcher, so that you have the minimum reflective power, means you have to get the maximum out of it. But the matcher is located outside the reaction area, so you only utilize the information outside the power. But there are a lot of things happening inside the chamber. So about matching, matcher, conventional matcher, cannot use any of this information. So we used reinforced learning based on the sensor data out of it. So this is the result. So this is conventional, how many iterations needed to have the match compared to reinforced learning, just 5, 6 times, and we are able to find that. So this is a very interesting example we want to utilize in the process control, not only just the matching, for entire everything. We are not there yet, but we are getting there, I believe. Okay, so I go back to this original. I'm very good on timing, 1 minute and 40 seconds left. So I'm going back to the original. Equipment perspective, there are many different times, the types of the data sources, all of them needed, and we need to have the foundation model. Why? Because process engineers, they tweak the recipes all the time, and even the same recipes, because of the tool status, and when did you do the PM, time difference shift, everything changes. You cannot use the same fixed task-specific model over and over again. Foundation model is needed because it needs to be adjusted along the way. Multi-modal foundation model is really important, and to have this diagnosis, forecast, and control. And we found that reinforced learning is a really good way to have the good control compared to traditional DNN and other metrics. Industry requirement, this part, okay, unfortunately data not showing. This is something I want to show with Professor Mitra, because what we need is, first, data needs to have the standard format. You can name how many different equipment vendors, OEMs, are there out there. There are a lot. And imagine that all of them, they are using completely different format of the data. So it's a mess for us. And then we have to force them to follow our own way of the format. And I believe TSMC will do the same thing, Intel will do the same thing. So that means every fab will have the separate way of handling the data, and then they have to develop the different thing. So instead of that, if we have the standard throughout the whole industry, it's much more easier and transferable for the OEM perspective and fab perspective. And unfortunately, we cannot just share all the data to outside. So what we do is we build our own cloud. So whoever have access inside cloud, they can utilize and use the data to do the analytics, to develop the new model and so on. Okay, so this wraps up my entire talk. So again, The key message is RAG, domain expert, and multimodal, and the foundation model, and knowledge graph, and so on. Okay, thank you.
Thank you, Dr. Park. Questions?
Can you hear me? All right. Yeah, perfect talk. I really like the approach, and I'm really curious about frequency and time, because these time series are like from nano down to femtometers, I guess, and current like inference times are like few tokens a nanosecond, I guess,
Yeah.
or microsecond actually, excuse me. So this thing doesn't work live. From what I understand, you pre-train it, build the foundational models, and then you try to use them and predict it like early on, not in real time. And then when you use GraphRag for the data that you stored historically, I suppose you label like the sensors from where the data comes from, and you try to aggregate the data from like local waves, fluctuations, to like more global. How do you like integrate and consolidate the data from different sensors into one coherent sort of memory/analysis system? Thank you.
Okay, great questions. Thank you. I hear the two different questions. First one, the foundation model times they don't work. I don't want to say that. It's not good enough to use for control yet. I guess they never used this level of the microseconds data before, so it's understandable. Even with the fine-tuning, pre-training, probably not good enough. We're trying to collaborate those, the founder of the foundation model, to provide some level of the data so that they can tune and make it much better user for our applications. We hope we can get better performance in near future. And about the second question, that's a very good point, because the encoding has to be different compared to text or other things. And just not text, like alphabet A is A no matter what, but 0.1, the value, it has completely different meaning based on the sensors or when. So this is a really good question. So we are trying to, so I can answer that there's no correct way or proven way. We are just trying to do a lot of different approaches. And normalize, as you can see, this is one of the easiest way. Okay. Yeah, go ahead.
Hi, Christopher Nguyen here with Itomatic. I'm also a co-lead of the foundation model working group in the AI Alliance, where you're trying to promote the idea of a industry-wide standard or convention for easier data interchange. There's one particular initiative in the AI Alliance called the Data Catalog, where we're trying to do very much exactly that, but also, in addition, to try to gather things like the data sets that can be freely shared, de-anonymized, or that you wouldn't make publicly available. In particular, the time series foundation model is a particular effort there. Do you think that's something that you would be considering collaborating with the AI Alliance companies on?
Oh yeah, that definitely. When it comes to the standard, we are not just working as a one company. So I'm working through the semi industry. So there's an organization called Semi. So we are using that, and I'm leading one of the task force about this particular task force. It's called Ikimban data publication. That is definition of the format of the data from the Ikimban. But definitely we can work together to have either working with the AI Alliance or you guys work together with the Semi. Definitely, yes.
Great. We have time for one more question. Anybody? Oh.
By the way, I have panel session tomorrow at 11 something, so we can discuss more.
Thank you for the presentation. For the time series data, have you considered to construct some kind of a temporal information as a way to capture the time information, which could be used as part of the control parameter?
Yep, definitely. One of the methods I was trying to use is, instead of having the two-dimensional the chart, I tried to make the three-dimensional like the mapping, and then I can treat as an image rather than just time series data. Also, that requires how I'm going to normalize all different data sets and so on. But one of the difficult part is these days, majority of the process control using the, as I explained, EPD, there's no specific time. The duration is all different. Basically, you have distorted images for every wafer. It's a little bit difficult. I couldn't find the solution yet. I tried, but not yet successful.
Great. Thank you once again, Dr. Park.
Thank
Another
you.
round of applause.